Good morning, good afternoon, and good evening. I am Viral Vigela, and I'm the account manager for X-ray CT technology with Rigaku. I'm here with our co-presenters, Angela Criswell and Aya Takase.
Hi, everyone.
Thank you all for attending Rigaku's webinar series, Ask the Expert. The best way to learn something new is talking to an expert. Our series will cover various topics and will be joined by industry experts to help us better understand CT techniques. Today, we want to welcome Dr. Philipp Eichheimer, who is the Filtration Business Manager and Application Engineer at Mat to Market, as the expert. He'll be discussing how to make R&D cycle more efficient using X-ray CT data and filtration applications. But before we start, a few housekeeping items. As far as today goes, this is going to be an interactive session, and I'll be posting relevant links in the chat window. We'll be taking your questions live during the webcast and answer them during the session, so please don't wait until the end to ask. As usual, please submit those questions via the Q&A button at the bottom of your screen. We won't be monitoring the raised hand function, and we'll try to answer as many questions as possible during the webinar, and any unanswered questions will be responded to after the webinar is completed. If for whatever reason you have difficulty viewing the webinar live, please note it is being recorded and you'll be able to watch the recording beginning tomorrow. With that being said, let me turn it over to Angela and Aya.
Thanks so much, Viral, and thanks again, Philipp, for coming back and doing another webinar with us. I'm pretty excited about today. So I'm going to stop sharing. Are you ready to share your screen?
Yep.
Excellent. I see it. All right, so just like in our usual previous episodes in Ask the Expert, we're going to ask Philipp a few questions. And to start it off, the first question is, Philipp, how do we use CT in filtration applications, and what are the benefits of using it?
Thank you. First of all, good evening or good day for all the others in the US time zones. Thanks for having me on this webinar series. Yes, the question addresses a very important feature that structural images include, especially CT, provide a valuable source of information to understand filtration-related properties on real filter media. These information can be used in combination with geodetic to optimize the filter media performance in a digital way. At the beginning, the filter media undergoes the structural imaging process, whereas in the case of a micro-CT, we obtain a three-dimensional representation. However, in some cases, we might also crash into some resolution limitations. Therefore, it is also possible in geodetic to have FIB SEM data, which go for even lower resolution in the nanometer scale, or just SEM resolutions. But in this case, we also only feature 2D images. But also this can be resolved in geodetic if we give additional parameters, for example, like porosity or grammage. So we are also here able to generate three-dimensional representation. In the second step, when we go for this imaging, we import the micro-CT images into geodetic, and our software offers here a wide variety of image filters to rotate, crop, or even to some extent improve the quality of the scans. For example, when a lot of times we have ring artifacts or noise somewhere in the images, we can to some extent get rid of this in our software. In the process then, the image stacks for the micro-CT undergo segmentation. So this means that we assign pore or solid phase to the grayscale image. And here our software, of course, provides the classical segmentation algorithms such as ODSU or k-means, for example. But additionally, we also offer artificial intelligence tools for segmentation. So these apply then pre-trained neural networks to the image. And here the user labels the pore and solid phase by hand. And this serves then as the label input for the neural network. This is especially useful when you have segmentations of images where you have some same refractions or binder included, but here we'll give some more information later on in this presentation. After the model is then finally digitalized, geodetic offers a large variety of analysis tools to characterize, and to predict geometrical and physical parameters. And this opens up new possibilities to optimize and to create new materials, and only to manufacture the prototypes with certain filtration relevant parameters, and also to obtain new understandings and knowledge about your filter media. So to conclude, the digitalization of your product development process with Geodict results in a fast, cheap, and sustainable workflow to improve existing media, and this reduce the time to market performance significantly. Are there any questions?
I had a question. As you were talking, I was kind of looking up what we could kind of talk about, but there is a question in the chat that I'll mention first. Are there limitations on CT data that can be used for these type of analysis with Geodict? What are the guidelines for collecting CT data that can be used for filtration simulations?
Yeah, so in general, to use our software quite good, we have like a rule of thumb. So the smallest fibers, so if you talk about fiber structures, should be resolved by 3 times the voxel size. So this is like to have like a good representation in the software. And this limits us, I will also talk about this in a couple of slides. This limits us to the smallest fiber, about 1 micrometer, as we have, like when we have very good conditions, we have micro CT resolutions of 300 nanometers. So roughly 1 micrometer is like the limitation we have here. If there are smaller fibers like nanofibers, we then move on to FIB-SEM or SEM images to have like a better representation. And of course, the mixture of the fibers is also quite important so that you get some representative elemental volume here.
Yeah, the mixture of the fiber is important in terms of getting better representative samples. So it's definitely helpful. I think we can go on to the next question. I'll save my question for later.
All right. So our next question for Philipp is, what are the filter properties that you can characterize for filter media from CT data? And which of those are really the most important to consider?
Yes, so the CT data gives us the unique opportunity to digitalize a 3-dimensional medium from a small image. And once the data is imported and segmented, we can use, as mentioned, different modules in Geodict to analyze and characterize several properties. On this side, I focused on the geometrical parameters, but the list can also be extended for physical parameters, which also characterize to some extent filter medias, for example, when airflow or with pressure drop. And some of the geometrical properties we show here are also can be easily determined experimentally, such, for example, the media thickness, which can be measured optically, or the porosity can be measured easily in the laboratory. However, some of these, such, for example, as the fiber diameter distribution or fiber length distribution, which are highlighted here, are even very tough to get experimentally or like impossible. For example, when you think of the fiber length distribution and the fiber curve several times through the inventor volume, this is like, for example, yeah, not the way you would, for example, look at these yeah, fiber structures or geometrical patches. To generate the fiber's digital twin, the parameters highlighted here are the most important in my opinion, because they provide the input parameters for the fiber geo, which is our structure generator. And by knowing these parameters, we can generate a digital twin. And in this regard, then utilize and change the parameters within the structure and find the filtration performance we have for new filter medias. And then we can run parameter studies and find the best parameters which you can use and to get knowledge of the new filter media and produce them and manufacture only the digital prototypes we have, like in we found met our suitable scans.
Many of those look familiar to me. We calculated them in our deep dive series for filtration.
Well, Philip, I was just wondering, if your fibers are not cylindrical or spherical, can we still use the software to calculate them?
Yes, so ideally, of course, we have pre-trained neural networks, which we apply to the micro-CT data, and they're most suitable, like, of course, when you have like cylindrical fibers. But in the newest version, we also feature the ellipsoid shape, for example. And when we have like a segmented image, for example, which we can also do with odds or k-means, this is like not an issue in the software. We can also characterize, of course, the porosity and all fiber diameters, because then it goes from the black and white, so for the pore space in the solids. So this is like not an issue to have also additional geometrical features, except for the like including the cylindricals, of course.
No, that's great. Thank you.
All right, so we'll head to the next question for Philipp.
Mhm.
Oh, surprise.
Well, next one is a question for the audience.
Yes, for sure.
Okay, so let me start the first polling question. So the question for the audience is, which characteristics of a fibrous filtered medium are you most interested in? The first choice is fiber diameter distribution. And the second one is fiber length distribution. And the third one is fiber orientations. It could be none of the above, then you can choose other. I'm gonna give you guys to think about it for a second. It's funny that we can see your answers coming in real time, and I can feel that you're thinking. About a half of you voted. I'm gonna give you a few more seconds. Okay. I'm gonna close the poll in 3, 2, 1. It's pretty split, so I'm gonna share the results. So the fiber length distribution and the fiber orientations, those were the most voted, about the same numbers. And then the fiber diameter distribution and the other followed.
Yeah, this is also what I would, for example, expect from the answers, because of fiber lengths is nearly impossible to do it without digital tools, because sometimes the fibers really curve several times into the media. The same for fiber orientations, because we have thousands of fibers. So this doing by hand is nearly impossible. So you would always go for digital tools in this way.
Okay, so I guess this was expected. I'm gonna stop sharing the results and let's go to the next question.
Okay, so the next question, this one's for Philipp. So what are the biggest challenges, Philipp, when using CT data to study filtration processes?
So the biggest challenges when we deal with micro-CT images is to find a suitable resolution to resolve all of the relevant features. We talked about this some slides ago, and most of the micro-CT devices have a minimum resolution of around 300 nanometers in the best cases. So when we use then the rule of thumb in the software to have like 3 voxels for the smallest fiber size, we end up for roughly then 1 micrometer, which is the lowest limit we can go with the micro-CT approach. Sure, we hope that the CD providers will enhance or lower the resolutions in the future. But when we have like lower resolutions, of course, in the fibers, we need to go to FIB-SEM or SEM representations, which bear then additional challenges. As I already mentioned, for example, in SEM, we only have a 2-dimensional representation. So we need additional parameters to characterize the depth of the media, so like for a 3-dimensional representation. A second point we consider is the quality of the scans. So we often see with our customers and clients, which do not always conduct the samples by themselves, so they have service providers for that. That noise in the pore space or artifacts are sometimes present. However, Geodict has state-of-the-art image filters to improve such scans, but in general, an initial good scan quality gives the best start for reliable analysis. And then a second point or like a third point to consider, that in some filter media samples, we have fibers and binder. So, and binder, for example, has often the same density or refraction as the fibers. So it's quite challenging to analyze the fibers without the binders and even to have like a segmentation here. And here comes the AI segmentation into play, which resolves this issue very easily. And in our software, we have this binder AI functionality, which detects the binder, and then you can easily remove the binder from the sample from microCT and purely analyze the fibers. Additional problems are also when we have the presence of two fiber types with nearly the same densities. So also here we have quite challenging tasks to analyze both fiber types. And this is also resolved when we have our fiber find AI, also the artificial intelligence tools here. And last but not least, the combination of several layers of different diameters can be challenging. As we see here in the image on the very bottom left. Here we have a very fine layer, so like mostly a nano fibrous layer in combination with a much coarser one. So, and this, of course, when we have a microCT image here, results mostly, as we can also see there, in not representative elemental volumes, for example. We have like a nice scope of the nanostructure, but we only have two fibers of the core structure. So here to run analysis is not very solid in this case. To resolve this issue, we would, for example, do scans, if it's possible, with a good quality from each of the layers, and then we can stick them together in the software. So this is possible, and then we have a good quality, and we can also have a good analysis later on that. Are there any questions?
I guess, what is the challenge in doing multiple layers over and over that you're doing? Is that how time consuming is that?
So in time's perspective, mostly it's quite efficient when you have like this sweet spot where you have, for example, as we mentioned, for example, with several layers of filter media, we have like mostly a very large extension in the Z direction. So we need to check here them with the microCT. But once we have the images into the software, the segmentation, especially with the artificial intelligence tools, is very efficient. You can also save later on the label matrix. So if you have similar microCT images in the future, you could, for example, use also the pre-trained neural network and save even more time. And yeah, very lastly, we of course have also like the capabilities to go with the software in the cloud. So for example, if there are hardware limitations which you are facing sometimes when we have very large data sets with a very small resolution, could also, for example, use the software in the cloud, which then borrows us the capability to have very large hardware without purchasing them by ourselves.
Okay. And there was a question that was kind of similar along the lines, like how long does it take to simulate a digital twin for filtration simulations? And what are some of the properties we need to kind of set in terms of parameters about contaminants and fluid for filtration simulations?
Yeah, so like when we have like the digital twin, this mostly depends on the complexity of the filter media. So it's just consisting of two fiber types and one layer. It's rather fast. If you have then several layers, binder and different fiber types, of course, it gets a bit more tricky, but it's possible in the software anyways. The same when we then, for example, predict parameters for the fluid, we give like normal parameters like densities, viscosities. So we can specify if you want to simulate air, water, brine, whatever you can think of. The same when something we have in our database, which there's some fluid not present for your simulations, you can easily add these kind of fluids and specify the parameters for that. So there's no limitations in this way.
Okay. Thank you.
We'll go to the next question now. And one of the things I really liked about the software was that you already have some preset distributions of particle sizes that makes it pretty handy to do the simulations as well. So your software covers a lot of bases in that sense. So the next question for you, Philip, is how do you use CT data then to model and design these filters?
Yeah, so this is then the question for a general workflow the software emphasizes. And as mentioned in the beginning, we always start, of course, with the input of data. So this can be on two ways. The first way is like the classical when we have, for example, micro CT images, which we can use. We can directly simulate on a micro CT images, gives us the real structure. But what we already mentioned is like then to do optimization studies. And for this, we need an optical or digital twin. If you're in a manufacturer and you know all the parameters like porosities, the fiber distributions, fiber lengths, and so on orientations, then you can directly use our structure generators to generate the structures. But if these are unknown, we have to rely on micro CT or structural images in general. And then we can use the analysis, for example, the FiberFind AI, and we obtain all these kind of parameters I mentioned in the second slide, the diameter distribution, the orientations, porosities, and so on. And this we can feed then as input parameter into the structure generation. So this leads us then to do the second step. We have then this digital twin. We can use the data and go from this point to the modeling part. So here we change then some of the parameters. We change either the geometrical parameters. So for example, the solid volume fraction, we change some of the diameters and we see what is the effect on the filter performance. Here we solve with classical CFD methods. So we have Navier-Stokes equations, and we have then afterwards to simulate filtration, we have particle tracking, where, for example, additional effects like drag, diffusion, electrostatic forces can be applied. So this is then when you go really in the prediction of physical parameters. Very interesting also for the filter media would be like, for example, to have deformation in the process when, for example, the filter media is compressed, which then, of course, changes the flow velocities and the pressure drop, which, for example, in some of the processes is applied to the filter media, or like when you have usage of the filter media. So this then opens up various types of applications here. And what to do here in this process, you want to investigate and get knowledge about the filter medias. So we create then digital prototypes when we do optimization studies and find in the loop parameters for desired properties. And this gives us some of the best performing digital prototypes. And we only, instead of like trial and error procedure, we only produce the prototypes which met the desired parameters in the software to have like an increased process development cycle. And to sum this slide, we can significantly shorten the development cycles with automated simulations, and we can enhance and digitalize the product development to save really time and costs in comparison to the trial and error procedures where you manufacture and test the filter media in the beginning and then to find out that it doesn't match your required performance. And digitally, you can do this like with various hundreds of geometries and then only produce the hot candidates on the test bench. Are there any questions?
I think you answered the question for this one in terms of just saving time and being able to have multiple simulation samples available and only picking the right ones that actually matter to you. So it does certainly can minimize a lot of time and money in terms of actual live samples that you're not using because you're simulating most of it already. So start the simulation process over a weekend and get ready for an actual live sample comparison on Monday or Tuesday. And you can minimize the correct candidate, I guess. So definitely really helpful in that process development. So no questions here. We can go on to the next one. Polling question.
So the next one is a question for the audience. So let me start the question number 2. Okay. So the question for you is, which aspect of the modeling and design process of a filter media is the most challenging for you? So you have 3 choices in other. The first one, data acquisition and image processing. The second one is the usage of simulation tools to predict the filter performance. And the third choice is the analysis of relevant properties from digital models, or maybe none of the above. Okay, so the answers are coming in. We're about a third of the way there. About a half. I'm gonna give everybody a few more seconds. Again, it's pretty split evenly.
Right. Right.
Okay, so I'm gonna close the poll in 3, 2, 1. Okay, I'm gonna end the poll and share the results. So it was coming in pretty even, but now data acquisition and image processing ended up being the #1 vote. Then usage of simulation tools to predict the filter performance, #2. And the last one was the analysis of relevant properties from digital models.
Yeah,
Does this match your prediction, Philip?
Yeah, to some extent. So I would like thought that, for example, the prediction of the filter performance would be like the first or the most important aspect here, because like especially for filtration, there is no other software which has like a predefined workspace which is really dedicated for filtration. Like Angela already mentioned, we have mostly everything which you need in the filtration process. Predefined particle size distributions, sketches, everything is ready for the filtration application. But yeah, on the second place, I'd also the data acquisition, because like it becomes really challenging when you go for filter media applications to have like either the micro CTs or the structural images ready, and then mostly to get like a 3-dimensional representation, which also covers then or like is reliable or comparable to the measurements actually you perform in the laboratory. So these are the most challenging I would also see here.
Okay. I'm gonna stop sharing and close it. There you go. Back to you, Angela.
All right, so we will pass on to the next question. And this is our lightning round. So if this is your first time to one of our Ask the Expert series webinars, this is where we get to ask Philipp a few questions to get to know him a little better that aren't necessarily related to filtration applications. So just a quick round. Philipp, where did you get your professional degree?
So my bachelor and master's I did here in Germany at the University of Mainz in geoscience and numerical geophysics in the master then, and then moved on to do my PhD at a different university in Germany, purely on geophysics, numerical geophysics, with strong focus on numerical flow within rocks or like also porous media. And here I did also like 6 months abroad in Japan to have like an insight on micro CT. So I conducted micro CT images and also measured material permeabilities. So also get like not only the numerical side, but have also some experience here on the experimental measurements and the challenges you face there.
That's great. What makes you a perfect fit for a company like Mass Market doing this? You checked all the boxes. If you hadn't have gone into your current field, what else would you have done instead?
My childhood dream was being a pilot. So I like to travel, see different cultures. Already went for the assessment center, but I did not pass. So then search for another direction or plan B, and then happy to did my plan B because I'm very happy what I'm doing.
Yeah, obvious pilot geophysics. Yeah, very cool. And flying's pretty fun too. We're actually really pleased that you found your way to this field and we get to work with you. So that's great. What field do you see benefiting the most from this type of filtration simulations that you're talking to us about?
From my point of view, is the air filtration very challenging, or gas filtration in general? Because we have here very fast flows, low viscosities, sometimes turbulence effects or additional effects, for example, electrostatics, which you don't need to consider that much in the fluid application. So this is like very challenging. I like challenges in several ways. And in general, of course, the application is for our air we breathe around. So this is like something we do for our health. Yeah, but it becomes more interesting also, like, for example, if for fluid filtration, when we deal like in the next couple of years with like the microplastics. So this will be also something I will face in the next years and will be one of the features we need to think of then later on.
Yeah, absolutely. And what changes or developments in the filtration industry do you think we'll see in the next 10 years?
I think in this regard, like, we move towards digital solutions. So in a lot of like development cycles, there's still this trial and error procedure. We have the tools like, for example, AI, which takes a lot of work from our side. So for example, for segmentation, which is now for very challenging phenomena, like I already mentioned, like we took our several filters, and now with AI, this works like when you paint the solid and the fluid phase, and it's working pretty well and solves a lot of problems we had like in the last years. And in general, like the workflow I mentioned, from the digital prototypes over the optimization, these are like fields where the artificial intelligence can take over a lot of tasks in the future.
Absolutely, yes. And our last question for Philipp is, what's your favorite science podcast or show?
It's a very specific in German. So it's a physics podcast, which discusses everyday physical phenomena, which I find very interesting when you look at the physics around you and not like the very space rocket science, just like the physics around you and daily problems.
Very nice. Very cool. So thank you so much for letting us interrogate you a little bit, Philipp.
No worries,
And with
thanks.
that, we will get back to the regularly scheduled program, our webinar on filtration simulations. Okay, so the next question for Philipp is, how do you scale simulation results from the media, let's say, to your complete filters?
Yeah, so a huge challenge in the development process is always to extrapolate parameters which are obtained on smaller scales and to transport the knowledge to larger scales. In this case, we see here some scales which the software is able to cover. So yeah, the main focus on the software, like when in the beginning, has been the filter media. So we can simulate here when all the fibers are resolved, we can import images, generate data, and simulate really all the effects on the filter media. But what is the real challenge is to have the findings we get on the filter media to then import to single pleats or like filter elements, which are also possible into the software when we import, for example, CAD data, where we have complete filter elements also with housing. And from the very recent pandemic situation, we are also capable of doing room scale simulations where we use, for example, an air purifier and can there run systematic studies on optimization where you put the air purifier for the maximum performance, or like to reduce the operational costs when you optimize the air cleaning rate. So this is something we are all capable of, and it has something in common, because at this scale, so like when you go larger than the filter media scale, you cannot resolve each fiber anymore. So you have to come up with some ideas, and the idea in general is like here that we simulate, for example, from the here marked in red, like for the single pleats, a porous layer. And this porous layer then, of course, does not feature the fibers anymore, but it needs to have some parameters or properties which are related to the filter media. In this case, then we can, for example, either from flat sheet experiments, which we obtain from the experiments, or from filter media simulations, we can obtain effective parameters, which we set then as the input parameters for the porous layer. And this gives us the opportunities to effectively simulate also the filter media effects on a larger scale. Here we have, like in the last years, it has been like a tedious process where you had to run several simulations to obtain these parameters. But in the newest version of Geodict, we have like an automatic calculation of these parameters. So you don't need to have like very experienced in the software or simulation field in general. When you run a filter media simulation, we see here the filter clogging analysis, and this gives us all the effective parameters we need to insert into the filter element simulation. Here we account, of course, for both filtration regimes, the depth filtration of the media, and also the cake filtration, which we have then on top of the filter media. It calculates and detects the layer thickness, the Fmax, which is one parameter, for example, which is representative for the filtration efficiency, or like the filtration properties in general on the filter media, and the sigma, which is one parameter which we have for the flow resistivity, as well as, for example, clean filter permeability and so on. The diagram below shows actually what is one of the findings, or like the studies we conducted. So here we have, like in red, like a resolved simulation where we have really the fibers resolved, and we can generate the results which perfectly fit with the measurements. And then we use this effective parameters as an input parameter for a porous layer. And we see here that the plot or like the diagram in blue fits very nicely with the evolution here of the pressure drop over time. So where we have first the depth filtration, which is a very smooth increase, and then later on we go for the cake filtration, where the slope is steadily increasing, which gives us the normal S shape you would expect from filter simulation. And we showed here that the effective parameters which we obtain from the resolve scale can 100% reproduce the measurements and also the simulation. Are there any questions?
Yeah, I just shared, Philip, as you were talking, I just shared the FilterDict page from Math to Market website, so our attendees can go and check it out. I'm sharing the this white paper you were just talking about. I'm going to add that link as well. But the question was, how long do simulations take for full filters when you're going through a simulation process? What's a typical timeline we're thinking?
Yeah, so this has several effects we need to consider. So the first is like the domain size we have. The software Geodict is like, developed in that way that we can directly simulate on microcity. So we don't simulate on small domains like 100 voxels in each direction. We really simulate on 1024 voxels in each direction with no problem. But yeah, surely there's also the aspects of hardware. So which hardware are you using? Is it a local machine laptop, or if you use, for example, cloud capabilities? Also the parallelization of software which we offer here comes into play. And of course, the size of your domain. So like what, for example, when we have filter elements, we sometimes simulate 80 million particles per simulation, or like billions of particles per simulation. So this takes sometimes some time when you, for example, think of filter lifetime simulations where you have like steady particle deposition, and every time we have to reconsider the flow field. But what I would say from the experience I have is like that, for example, filter lifetime, when you have like a filter media with reasonable sizes and good hardware, is like 1 or 2 days, and you have a filter lifetime simulation. So when you go for a clean filter media, only want to have like the initial pressure drop or the initial filtration efficiency, this takes up to a couple of hours. So this is like not an issue at that case.
It's not bad at all. A couple of hours, that's, better than still doing it live.
All right, so let's head to our next question for Philip. All right, so this in fact is, I believe, our last question for Philip. So what is the optimization process, Philip, for developing better filtration products?
Yeah, so thank you for the question. I want to answer this question with a recent optimization study, which is presented in a nutshell, the results. And this study we conducted together with a German university in Heilbronn here. And what we did, we used a surgical mask here, and we conducted the micro CT with a resolution of 0.5 micrometers. And we clearly see here 2 layers. So the first one is a coarser layer, which is here on top, and a finer layer, which is on the bottom. And what you could infer from this case is that the coarser layer is more or less responsible for the stiffness of the filter face mask, and the finer layer is mostly responsible for most of the pressure drop and also the filtration capabilities. What we did then first was to have like reference modeling. So what we see here is the filtration efficiency on the y-axis against the particle diameter. And in purple, we see here the experimental measurement on the mask, which has electrostatic charge on that. That's explaining the high initial filtration efficiency we are seeing here. But as we don't know the electrical charges or like the charge distribution, we decided to decharge or discharge the mask. And this is done with isopropanol in the beginning. So this is like the study of Sebastian Berger from the University of Heilbronn, where he published the measurements and the procedure. And we discharged the media 24 hours with isopropanol. So all the charges are gone and we can purely simulate the mechanical filtration. And what we see here is then in green, when we have a discharge of 24 hours, the loading curve or like the efficiency over all particle sizes experimentally, and we see in red the simulation with geodict where we have no electrostatic charge. And we see that we have a very good fit over all particle size diameters. So we have like a very good comparison between the experiment and the simulation. However, of course, simulations in geodict, as I already mentioned, are also possible to simulate the electrostatic charge. So we could, for example, just use the different electrostatic charges of the filter media until we match the original purple points. So but this would be like out of the scope because it's just a fitting of the simulation tools. We don't know the real value. And then to first of all have the reference of the micro CT directly. And then what we did was the second block we did analyze the structure, and we obtained solid volume fractions, the mean fiber diameter, orientations, and so on, and created a digital twin. And then when we move on from the analysis part, I mentioned some slides ago, and we go the next step in the workflow. We want to model physical parameters. So in our case, we modeled the initial pressure drop and the initial filtration efficiency. These are the 2 parameters which we considered as the characterization of our filter media. And then we move to the last point is the workflow, where we created digital prototypes, which, for example, suit then specific needs or requirements we have. And what we did here, we just ran a parametric study where we varied the solid volume fraction as indicated here, the mean fiber diameter and the media thickness in Z direction. We added some statistics on that. So we have for each geometry, we have like a random seed, which we can iterate. And then we have the same stochastics, but we have different variations of the stochastics to get like, just a solid background in the statistics here. And this have been a total of 540 simulations we run here. And for this, we use the capabilities in geodict to run Python scripts and to automate the simulations. So you don't need to click each of the simulations by hand. It's done automatically with scriptings. And this is what Varel already mentioned, like in the beginning. So for example, you could send out the 500 simulations on a Friday, and depending on the runtimes, you would collect most of the results on Monday, Tuesday, or Wednesday, depending on the hardware or the sizes of the geometries. And then you can analyze all these 500 simulations to find the best fitting structure, which suits your needs. And this is what we show here on the slide. So for one optimized structure, we said we want to have the same filtration efficiency as the reference. So we don't want to lose any filtration efficiency at the beginning. And we found a sample which is 10% lower in the initial pressure drop. And even we saved 7.6% of solid volume fraction. So of course we had a smaller fibers and therefore less material. So we have less pressure drop and we consume less material and keep the same filtration efficiency just by running a variation and over several parameters. And then on the second point, which we discuss here, is like that when we say, for example, the filtration efficiency might change, we can get better or can even get worse. We could, for example, even optimize for 21.5% less initial pressure drop and have also less material. But of course, on the bad side here, we see also like that the filtration efficiency decreased. But yeah, it depends on the scope you want to optimize. If you want to, for example, optimize purely on the initial pressure drop, we would take the second nice structure for the testing and manufacturing on the test bench. But if you go then just want to see, okay, we have an existing mass and how can we improve, we would definitely go for the first one. So here, the full open access publication is accessible, which we published this year in the Chemical Engineering Technology Journal. And this shows exactly what the workflow in GeoDict is all about. So you can really run several simulations and find the best suited material and then directly go for the manufacturing step without trying, like we would never try 500 manual procedures of the filter media to find the one, to have like optimized features on that.
Sounds expensive to make. Yeah.
Yes.
Yeah.
I think expensive, time consuming, and also just, I think the challenge here is not, setting up the simulations and parameters and kind of letting them go and collecting data. It's storing that data and having that infrastructure. Sounds like a bigger challenge than anything else, not actually going through with setting up the experiments in GeoDict. But the question here is, I guess, how can we optimize it in terms of media thickness and filter diameter? What do you recommend for the step sizes for optimization process for these experiments?
So the step size, I would always like focus on the application. But in general, like we are like not limited to any number. So you could, for example, use also very small step size and have thousands of geometries you want to consider. So it's just like, how to say this, find a sweet spot between how many simulations you want to run and what is suitable. And what what the software gives is like, it gives like a performance of the filter media. But what is also like a very challenging part is, of course, to produce the filter media. So of course we can simulate filter medias, but it's always the question if it's like also suitable in the manufacturing process. So here, for example, it's always like recommended to have like also the step size or the ranges in suitable production lines. So for example, it's always like challenging to have like very, very small fibers. Of course, the pressure drop is less, but they are also very challenging to manufacture. One point also to comment on is like the simulations we did in this study was sequentially. So we have like each simulation run after another. But if you would consider, for example, to have like 500 simulations using the cloud, so you could run all at the same time. So you could have this 500 simulations within a couple of hours, because it's not a filter lifetime, it's just initial pressure drop. So you could have thousands of simulations sent to the cloud, and within a couple of hours, you have these 500 structures analyzed, and you can directly obtain the results. So this shows again, like what is the potential of optimization and shortening of your development cycles when you consider, for example, 1,000 structures running in one day.
Yeah, that's incredible.
All right, so then we're going to head on to the next slide. Questions.
So the last question is a polling question for the audience. Okay, so I'm going to launch question number 3. Which advantage of the optimization process provides the most benefit for your application? So the choices are reduction in development time due to digital workflow. And the second choice is sustainability. And the third one is saving cost by reducing the number of prototypes. Or you might say other. Okay, I'm going to give you a few seconds to think about this. Coming in, about a half of you, I think, voted. I'm going to give you a few more seconds to think about it. Okay, so I'm going to close the poll in 3, 2, 1, and share the results. So I think, Philip, you had a pretty good prediction of what people are going to say, because not a lot of people are choosing other. So the number one, the voted answer was reduction in development time due to digital workflow. And the second one is saving costs by reducing the number of prototypes, then sustainability followed.
Yeah, so this is something, you would expect, and which goes also hand in hand to some extent. So the reduction in development time due to digital workflow, of course, goes also like when you, for example, reduce the number of prototypes, like the physical prototypes. Digitally, of course, you go for 1,000 of prototypes, but when you have like the systematic simulations, we only end up with, I don't know, 4 or 5 candidates you would take for a test bench. And this both saves, of course, the materials and the time, because the manual testing of 5 is not that time consuming, than have like 20, 30 or 40 or even more.
Right, exactly.
Makes sense. Sorry about that. I'm actually doing this from Germany too. I think I'm probably like 20 minutes drive from where Philipp is.
Yes.
Yeah, from
And
Canada a
It's
bit
like-
more, but yes.
Yeah. And I'm borrowing somebody else's office. It's getting late here, and then somebody came in to clean the
They're
Anyway,
trying
I'm
to kick you
gonna-
out.
Yeah,
What
right.
happens with live webinars, right? It
Yeah,
happens.
sorry about
Yeah.
that. Yeah, I don't have the sign I usually use that says, don't come
That's
in, I'm
right.
doing a webinar.
Exactly. Yeah.
Okay.
All right, so thanks for that polling question, Aya, and thanks for sticking in, both Aya and Philipp in Germany. I know it's getting late there. So that's going to wrap it up for our webinar. Before we go, Philipp is going to share a few more things about Math to Market with regard to this filtration simulations and such before we wrap things up.
Okay, thank you. So what we in general, like what I think most of the parts here, I think got clear from the filter media side. We can, from the filter media side, import nearly any image you could think of, like microcity, FIP, SEM, but we also had like shown also the tasks where we, for example, had images of deformed filter pleats, which we imported into the software and run simulations. And so there are no limitations, nearly no limitations on that. And then we have a lot of structure generators. So we talked the whole presentation about fibrous media, which is like mostly common in the air and fluid filtration field, but we are also capable, for example, simulating membranes, which is a large application area. We have, of course, woven materials. So we have also like a weave geo where we can generate woven structures and then have combinations of woven structures with fibrous media. So this is not a problem. We have larger scales, which I mentioned, like pleats and support meshes. Foams is also something we can consider. So we have a very large variety of structure generators. So also when you think of DPF, GPFs, we have granular structures where we have higher temperatures and fibers are not suitable anymore. So from the modeling part, which shows the filter media, we don't have that much restrictions and have a huge variety which you can cover. Then the analysis I mentioned already on one of the slides. We can analyze media thickness, diameters, orientations, grammages, also some physical geometrical parameters like bubble points, which are like very popular in the metal wire communities, percolation path, which is a purely geometrical parameter. And then we move on to filtration experiments. I mentioned. So in the software, we have a dedicated framework for filtration. So you don't need to stick together different toolboxes and working packages and softwares. It's everything in one software. We have single pass, multi-pass tests after norms. We have standard testers, as mentioned, as default settings, which you can choose from. We can have different effects, electrostatics, Brownian motion or diffusion. We can account for nano fibers where we have slip lengths, which you can account for. And this gives us opportunities to have really optimization studies for filtration. And then on the filtration simulation, of course, we're interested in filtration relevant parameters, which are in our case, the initial pressure drop evolution over time when we have like filter lifetime simulations, filter efficiencies, capacities. We can have filter classes tested. And what is also most or like very interesting is most penetrating particle sizes. So besides that, most of the parameters can be accessed with our Python IPA. So if you have the need for individual analysis, there is nearly no limitations to have like that afterwards. So many more features are on that. Some of the case studies I just mentioned was like one case study where is the identification of fiber characteristics of a filter media based on the artificial intelligence tools I mentioned. So this is a study of my colleague, Andreas Grieser, which pre-trained a neural network and shows here the application and the cover with the measurements. And then in this second case study is what I already mentioned, like the transform from the filter media to the filter element, which are the challenging parts of modeling and simulation, which is now optimized in the newest version of Geodict. Thank you.
That's very comprehensive, for sure.
Yeah, and I shared all the filtration examples and applications from Math to Market, as well as the technical reports and publications and case studies in the chat window. So our audience can access them as they please and take a look at them in more detail at their convenience. Well, I think that concludes this webinar. Thank you all for attending today's session. Join us next month. We're going to meet with Dr. Chandra Reddy to discuss designing CT image analysis for your research and what to quantify. That is July 19th at same time, 1 p.m. Central. Till then, take care and keep scanning.
Thanks,
Thank you,
everyone.
everyone.
Bye.
Thank you.
Bye.
Thank you. Bye-bye.